In this video, we learn how to calculate the change in Gibbs energy of a reaction. Alright, in prior videos we have seen the definition of the Gibbs energy, and we have said that you can calculate changes to the Gibbs energy simply as the change in enthalpy minus the temperature times the change in entropy. Now we see how we can apply this to a chemical reaction. There's not going to be a lot of differences here. Notice that in principle, for a reaction you simply write a subscript sub R to just specify that you're looking at a chemical reaction. And then usually we're interested in quantities per mole, so these will be all molar quantities. Alright, so notice that the two ingredients that you need are the change in enthalpy in the reaction and the change in entropy in the reaction, but we have learned how to calculate both of these things. Right? The change in enthalpy in a reaction is simply the enthalpies of products of formation, the enthalpies of formation of products minus the enthalpy of formation of reagents. And then the change in entropy will be the standard molar entropies of products minus the standard molar entropies of reagents. Okay, so let's see how these things would apply to just a regular chemical reaction like the hydrogenation of aluminum, which is a solid, with hydrogen gas to generate aluminum and then water, which is a liquid. We want to do this at 298 Kelvin because that's actually the temperature at which the data in which you have enthalpies of formation and third law entropies, that data is all at 298 Kelvin. Right, so then let's start with the enthalpy. The change in enthalpy in the reaction would simply be the sum of the enthalpies of formation of products minus the sum of the enthalpy of formation of reagents multiplied by the appropriate stoichiometric coefficients. That's what these nus are. Also, when we go to thermodynamic tables, those data tend to be at standard conditions, and that means that we're working with a pressure of 1 atmosphere and pure substances, and also they're given at 288 Kelvin. So that is, in principle, the only temperature that we can use to calculate this change in Gibbs energies of the reaction. Like the standard denomination is usually denoted with this, which means that in our case, because we're always using standard data, really our data is all going to be at the standard state. Again, 1 atmosphere of pressure and pure substances. All right, so for the reaction that we have at hand here, I'm not going to go through the calculation. We just take the enthalpies of formation, multiply by the stoichiometric coefficients, and then take products minus reagents. But that number happens to be 819 kilojoules per mole. Here the positive sign indicates that this reaction is highly endothermic. Okay? Now we also need the change in entropy in the reaction. Okay? And then this is just going to be the sum of the absolute molar entropies at standard and 288 Kelvin of products minus the absolute molar entropies of reagents at the standard state, multiplied by the appropriate stoichiometric coefficients as well. And again, this is something that is fairly easy to do. You simply go to the thermodynamic tables, get the entropies of products and reagents at the standard conditions at 298 Kelvin, and then you can calculate this. Right. Something that we can do is try to anticipate whether, for the process at hand, the change in entropy would be positive or negative. And what we see is that, well, there's two solids, but those do not contribute too much to the entropy. And then you have 3 molecules of gas turning into 3 molecules of liquid. Right? So we expect this change in entropy to be negative. Right? You're ordering the system. You should be losing some entropy, and you certainly can see that because the sign of the change in entropy of the reaction is 100 minus 178 joules per mole Kelvin. All right, so now you come to your calculation of the standard molar Gibbs energy of reaction, and you would just take that enthalpy of reaction that you just calculated, and then minus the temperature multiplied by the entropy of the reaction. Now, something that is important here is to recognize that there is a unit mismatch between the enthalpy of the reaction and the entropy of the reaction. Notice how the enthalpy of the reaction is provided in kilojoules per mole, but the entropy is in joules per mole Kelvin. right? So here what I prefer to do is to transform the entropy to kilojoules per mole Kelvin, right? So that would be minus 0.178 kilojoules per mole Kelvin. Right, so now this Kelvin cancels with that Kelvin, and then everything that you get out here will be in the form of kilojoules per mole. All right, so that calculation gives a number of 872 kilojoules per mole. Right, because that is a positive number, and we're working under constant temperature and constant pressure, then what this means is that this reaction should not be spontaneous as written. On the other hand, the reverse reaction, the reaction of aluminum with water to generate hydrogen gas and alumina, that actually should be spontaneous. Right, so this is how you would in principle calculate the change in Gibbs energy in a chemical reaction. However, notice that this calculation involves two different calculations, the enthalpy and the entropy. The question is whether there's a shortcut to calculate the change in Gibbs energy in a reaction, and the answer is yes. Okay, and we're going to explain what that shortcut is. The idea here is that Gibbs energy matches enthalpy, and entropy is a state function, right? So if that's the case, then the changes, the calculation of the changes only necessitates knowledge of the Gibbs energy of products and reagents, because those are your final state and initial state, right? So notice how for this state function, we've taken the enthalpy of products, enthalpy of reagents, and that change is what gives us the enthalpy of the reaction. Same thing for this state function, entropy of products, entropy of reagents, and there you have it, right? That's the change in the reaction. The question is there something similar for the Gibbs energy? And the answer is yes. Okay, I'm going to note this number down, that is 872 kilojoules per mole, because we're going to calculate it in a different way to show that this actually works. Okay, so notice that for the Gibbs energy of the reaction, you could actually do something similar, right? So you'll have here some sort of measure of the Gibbs energy of products minus the sum of the stoichiometric coefficients multiplied by a measure of the Gibbs energy of reagents. Right, the question is whether here we're going to have Gibbs energies of formation, much as what we have in enthalpy, or the absolute entropies, or absolute Gibbs energies, as we will have with the entropy. Right, so the idea here is that because Gibbs energy is an energy, and it's generally quite difficult to measure the total energy content of a substance, here we're going to be using the formation reference. Right, so what we will do is much as what we did with enthalpy. We said the enthalpies of formation of pure substances when they're just elements, pure elements like oxygen, graphite, nitrogen, the most stable allotropes of those elements. We set those enthalpies of formation at 0, and the same thing we're going to do with the Gibbs energies, right? So we're going to say that the Gibbs energies of formation of the most stable allotropes of elements are all 0. Then we will refer the Gibbs energy of all of the molecules to that common C level, and then we will be able to take differences with those relative Gibbs energies with much trouble. Okay, so here we're going to be using exactly the same argument that we had for the enthalpy, right? These are going to be Gibbs energies of formation. We don't have something like the third law, which set the 0 for entropies. Instead, we have to set the 0 ourselves, and we choose to do that with the Gibbs energies of formation. Right, so it turns out that there's tables in which you have tabulated Gibbs energies of formation for most molecules of interest at standard conditions and 298 Kelvin, so you can always use those to calculate your Gibbs energies of reaction in an easy way. Right, so here I am going to plug all of the numbers for this reaction. Notice that this would be, yes, the Gibbs energy of formation of products, which is aluminum, solid. We have 2 of those, and then 3 times the Gibbs energy of formation of water in the liquid state minus the Gibbs energy of formation of reagents. So that will be Gibbs energy of formation of alumina, which is solid, and 3 times the Gibbs energy of formation of hydrogen, which is a gas. Okay, so then we notice that aluminum is the most stable allotrope of aluminum, so that has a 0 Gibbs energy of formation by definition. And the same thing is going to happen for hydrogen. Hydrogen is a more stable allotrope of hydrogen, so by definition that Gibbs energy of formation is 0. So then what this means is that we just need the Gibbs energy of formation of water, liquid, and then that of alumina. And those values are minus 237 kilojoules per mole, and then minus the value for the Gibbs energy of formation of alumina, which happens to be minus 1582 kilojoules per mole. You do this and you find that this number is 871 kilojoules per mole, which is exactly the same number that you calculate with the enthalpy and the entropy within truncation error. All right, so in this video we have seen how to calculate the Gibbs energy of a reaction. There's two pathways. You either take the enthalpy and the entropy and combine them in this fashion, or you use the Gibbs energy of formations, which is a little easier, it requires fewer calculations, but they both provide the same number.